Thank you very much. I would like to thank the organizers for giving me the opportunity to talk about my work. So let's review some definitions and some facts. Let me start by just reminding what a conformal pseudo-Riemannian structure is. So a conformal pseudo-Riemannian structure of signature PQ, where we're assuming both PQ and greater than or equal to 1, can be introduced in two equivalent ways. One way, the conventional one, is to think of equivalent class of pseudo-Riemannian metrics of the same signature, which differ by a scale. So if you have a Riemannian, pseudo-Riemannian metric up to scale, or a class of pseudo-Riemannian metrics that differ by a scale, then you can introduce a conformal structure, or pseudo-conformal structure, which also we heard the name semi-Riemannian, conformal of a semi-Riemannian metric. Another way is to, perhaps a bit more geometrically, is to look at the null cones that are introduced by a choice of conformal pseudo-Riemannian structure, which is basically the cone that is formed by the set of tangent vectors that are null with respect to any pseudo-Riemannian representative of the conformal class. So this gives like a field of null cones over the manifold, and knowing this field of null cone is equivalent to having the conformal class of pseudo-Riemannian metric, because once you have the vanishing set of a quadratic form, you're able to recover the quadratic form up to a constant. So this, for this talk, I'm going to give a Finslerian generalization of pseudo-conformal structures. We're going to hear more about this in the mini course of this conference, and the reason is, can be sort of motivated, for instance, by a Finslerian point of view for gravity and light propagation, and there are some applications that are being pursued in mathematical physics and theory of integrable systems, just to define these structures, which I call causal structures, but also there's a community of that call them cone structures, or more specifically, people think about cone structures arising from Lorentz-Finsler metrics. We would like to just generalize this field of null cones that we get from a pseudo-conformal structure to a field of cones that are not necessarily quadratic. So they are sort of nice in the sense that they have non-degenerate second fundamental form, but they're not necessarily quadratic. They can be like a perturbation, or they can be something completely different. And because they can be quite wild, we would like to just consider a neighborhood of these cones. So we're just going to consider, because first of all, they're cones, we can projectivize and work in the projectivized tangent bundle. And then we're having like a sub-bundle of this, and we work in a neighborhood of this sub-bundle where everything is nice. We don't have any self-intersection, any singularity, and maybe it has multiple components. We consider just one connected component. So this is how we define it, that a local causal structure of signature PQ is just a codimension 1 sub-bundle of the projectivized tangent bundle, or an open set in the projectivized tangent bundle, such that each fiber is a connected projective hypersurface. So this would sort of generalize the notion of null cone in pseudo-conformal structures. And we further assume that the projective second fundamental form of this hypersurface, which is a hypersurface inside a projective tangent space at each point, is non-degenerate and has signature P-1, Q-1. So remember, the fibers are now in the projectivized tangent space at each point. And P plus Q is N. Equivalently, we're going to talk about the second fundamental form a bit more later. Another point of view is to say that this sort of field of cones locally can be expressed in terms of a vanishing of a Lagrangian or a Finsler function, which is defined on this open set U. We assume that it has in vertical, because it's defined on the cones in the tangent bundle, so its vertical Hessian is non-degenerate as signature PQ, and it's homogeneous also in vertical fiber coordinates in the tangent bundle. So let's also, now that we have this geometric structure, let's review some well-known solutions of equivalence problem, and then get to this causal structure. Remember that we want to distinguish geometric structures up to a certain local equivalence. For instance, this is the content of Cartan's equivalence problem. For instance, in Riemannian geometry, it's quite well known that having a Riemannian metric, there is a well-known connection called Levi-Civita connection, which you can build up on an ON principal bundle in your manifold. So Riemannian metric defines this G structure, or better known as an ON structure, as we heard in the previous talk. It's a type of G structure. And then on this ON bundle, you have a sort of a unique co-framing, which comes from this Levi-Civita connection. And it helps one, it basically solves the equivalence method for Riemannian metric. So to each isometry class of a Riemannian metric, there's a unique Levi-Civita connection that determines it and produces the fundamental invariant of the metric, which is known as the Riemann curvature. And you can use that to sort of distinguish the isometry class of a Riemannian metric. The other one is conformal structure of a pseudo-Riemannian or Riemannian metric is, again, it's a G structure, and you can use what's known as normal Cartan conformal connection on a certain principal bundle, which is principal P1 bundle, where P1 is the first parabolic group in this orthogonal group over your manifold, and then this helps one to find invariance of these structures, and they're known as Weyl curvature of the conformal structure. Then we have Finsler geometry. Finsler geometry, again, it's a generalization of Riemannian geometry, where you no longer assume your unit spheres are quadratic, and you replace it by some affine central affine hypersurface. And in there, again, you have the notion of connection on certain principal bundle over your indicatrix bundle, this bundle of unit spheres. And there are many of these. There are Cartan, Chern, Hashiguchi, and a few more. And then having that connection allows one to, again, find the invariance of these Finsler structures, which are known as flat curvature and Cartan torsion. And this Cartan torsion is basically the cubic form of your unit sphere, of your unit tangent vector bundle, or which are known as indicatrix. And its vanishing basically says that the Finsler is essentially a Riemannian structure. So what I did in my thesis is to do this for causal structure. So we have the distribution of null cones, and it turns out that, again, there's a notion of Cartan connection. Out the first two nodes in the Deakin diagram. And so there is this notion of connection of certain principal bundle, and one can find the fundamental invariance of this structure, which I call the Weyl flat curvature, sometimes I refer to as Weyl curvature, and the Fubini cubic form of these cones. So to point of your cone bundle can be defined in this way, that you differentiate your defining function in terms of y, which are the fiber variables in the tangent bundle, and form this expression. And because L is homogeneous, this one form descends to the projectivization of your null cone bundle. And we further assume that the vertical Hessian of this Lagrangian, this defining function, has maximal rank when you restrict it to the the null cone bundle. So it turns out that when you projectivize your null cone, so this is, first of all, remember M is n-dimensional, and then when you projectivize the null cone bundle, it's a codimension 1 subbundle. And it turns out that this one form defines a quasi-contact structure on this subbundle. What's a quasi-contact structure? It's a choice of one form on your manifold, which, because it's even dimensional, it cannot be contact. It's the next best thing, which is a quasi-contact. So this is 0, but this wedge product is non-zero. As a result, you can always find the characteristic curve of this, the characteristic direction of this one form, which is generated by a vector field satisfying these two directions. So it's in kernel of omega, and sorry, this has to be d of omega. So it's kernel of omega, and also it's d omega vanishes when you feed it with v. So here it's the exterior derivative of omega, and then knowing the expression of omega, and this is the definition of v, the choice of a vector field for this characteristic vector field of our quasi-contact structure is given by this expression, and this is nothing in case L is quadratic in yi's. This is nothing but the null geodesic spray of this metric. So it coincides with what you get as null geodesic spray in pseudo-conformal structures, but here we're working in a more general setting, and we're not assuming that this quantity, this vertical coefficient, is constant. It has constant coefficients, so it doesn't necessarily come from a metric. So now we want to go to now that we have these null geodesics, remember I'm defining null geodesics as something that foliates our projectivized null cone bundle. Or you can think of it as project them on your manifold M and think about, so it's I'm abusing the terminology. So when you're having these foliation by curves, I define a causal structure. This is a term that is used in sort of Twister school, the Twister community. A causal structure is called civilized if its space of null geodesics, which has to be 2n-3 dimensional, is a smooth Hausdorff manifold. And this quotient map is a smooth submersion. So this is our projectivized null cone bundle. And locally, of course, when you're around one geodesic, you can, in a small enough neighborhood, you can assume that this is always the case for a causal structure around a null geodesic. And remember that the null geodesic flow was basically the degenerate direction of this Hilbert one form. So again, this is d of omega, and it's defined this way. So that means when you're quotienting out by these, integral curves of this degenerate direction, you get this omega descends to the space of null geodesics, satisfying this rank condition, which is nothing but maximal non-integrability condition. That is, our space of null geodesics has a contact structure. Furthermore, I define a causal structure stationary if it has an infinitesimal automorphism that is transversal to this quasi-contact distribution. Quasi-contact distribution is basically the distribution that is given by the kernel of omega. So if it's transversal and it's infinitesimal automorphism, the causal structure is called stationary, or equivalently, you can look at it as a Riemann vector field in your space of null geodesics, which is an infinitesimal automorphism of the induced geometric structure on the space of null geodesics. And so this is the theorem, it says that given a stationary and civilized causal structure of Lorentzian signature with zero wall-flat curvature. Remember, there were two curvatures, sort of fundamental invariant for a causal structure. One was this Weil curvature, and the other one was this Fubini cubic form. So if this is 0, that means it cannot come from a conformal structure unless it's flat conformal structure. So if this is a zero-vol curvature, then the space of null geodesics locally has a Sasakian structure. The Sasakian structure you can think of as, natural cone over it is a Kähler metric, which I'm not going to define because I'm already, towards the end of my time. And I just give the main ingredient of this, which is the Chap-Salish notion of parabolic conformal symplectic structure. So we go to the space of null geodesics. It's equipped with what's known as a Lie contact structure. And then when you assume this transversal vector field, which is a transversal automorphism, you go to a hypersurface that's transversal to the trajectories of your killing vector field, and then over there you have another structure, and there are these complex geometric structures that you can cook up on the space downstairs. Basically, you have this bundle in there, and you have a complex structure, and you can take a section of this disk bundle, and you pull back everything to your space of null geodesics, and it turns out that it equips this space with a Sasakian structure. And the corollary of this is that if you start with a Lorentz-Finsler metric of flat curvature plus 1, then the space of geodesics, which is divided into time-like, space-like, and light-like geodesics, has basically this geometry that the space of space-like has a pseudo-Kähler metric, the space of time-like has a para-Kähler metric, and the space of light-like has a Sasakian structure. If the Lorentz-Finsler is geodesically simple and it's stationary. And again, this is a combination of the theorem that I showed and a result of Bryant on Finsler metrics of flat curvature plus 1, and sort of a change of terminology. These notions give similar results for flat curvature -1 and 0. So I think I'm out of time. That's all I had to say. Thank you very much.